Okay, moving along, number 4, is the color of the motorcycle helmet somehow related to the risk of crash-related injuries? One study found that of 899 motorcycles not injured in a crash, 491 wore black helmets, 377 wore white helmets, and the rest wore yellow and orange helmets. 333 motorcycles who were injured or killed in a crash, 213 wore black helmets, 112 wore white helmets, and the rest wore yellow or orange helmets. Is there evidence that color is related to risk of injury or death? So first of all, how many variables are we looking at? There are 2 variables. For each of these people, we know if they were injured or not, and what color their helmet was. So we have 2 pieces of information. So this is a 2-variable question. And second of all, they're all categorical, multiple choice type things. Like the 2 pieces of information we have are injured, yes or no, and a color. Like the pieces of information are not numbers that we have for each individual motorcycle rider. So we have 2 types of tests where there are 2 categorical variables. There's one where we split them into 2 groups based on their answer to a first question, and then we compare the proportion that give a specific answer in a second question. And the other one we have is chi-squared, where basically we make a table with all the options for one answer down one side and all the options for the other answer down the other side or across the top, and then fill in the table. Now, this one kind of has to be a chi-squared question because we have 3 options for one of the questions. When you split into 2 groups and then you compare the answer to a second question for the 2 proportion question, like it's really like you need 2 answers to split into 2 groups, and then you need just like a yes or no for the second question. Say like, are you a yes? Are you part of the proportion? Or are you no? Then like you're not part of the proportion you were looking for. So if you have these 2 multiple choice variables and they have more than 2 choices, it's basically got to be chi-squared. If there were only 2 colors that we were considering, we could do this with chi-squared or with a 2 proportion, and either test would work, and they should give similar p-values, maybe not exactly the same. But because there's 3 types of color that we're looking at, it kind of has to be chi-squared. So let's flip over to Minitab and fill in a table with that information. So I'm going to make a little table off to the side. So we're going to have injured and not injured. And then our colors are black, white, and yellow-orange. Okay, so how many black injured ones were there? So I guess in the question wording, the non-injured comes first. So there were 491 not injured black helmets, and there was 377 not injured white helmets. And then annoyingly, they say the rest were yellow or orange helmets. So we have to do a little bit of arithmetic. There were 899 total that were not injured. We subtract off the 491 black helmets and the 377 white helmets, and that leaves us with 31 yellow and orange helmets. Okay, so how did I get that? What did I say? Did I say 31? And I wrote 37, so it's 31. Okay, so how did I get that 31? Well, I knew that there was 899 total. And I took the 899, I subtracted off the 2 numbers we knew. So we'll have to do that for the injured column too. So there's 333 total that were injured. 213 wore black helmets, so we'll plug that in for black. And 112 wore white helmets, so 112 for the white. So we take our 333, subtract off the 213 that wore black helmets and the 112 that wore white helmets, and that leaves us 8 that wore yellow and orange. Okay, so we're going to run chi-squared on this table. So that was under stat tables, and then the chi-squared test for association. We have summarized data in a table. It's in the injured, not injured columns. And yeah, all that stuff looks good under our options. So let's hit OK. And we can see the totals they've given us. There's the 333 and the 899 to confirm I didn't make any arithmetic mistakes. The numbers that we typed in, the expected numbers, if it were true that these variables were independent. Our p-value is 0.012, and it didn't give us a testing level in the question. So I'm just going to sort of default assume that it's 5% if it doesn't give me a testing level. I'll try to be clear on the actual final exam what the testing level is. And 0.12, that's like 1.2%. It's less than 5%. So if our testing level is 5%, then we do have strong evidence of an association. These variables are not independent. So like looking at the table, it looks like the injured numbers are higher than expected for the black helmets and lower than expected for the white helmets. Just a little bit, but I guess that's enough difference to be a statistically significant difference. Okay, so that's that one. P-value 0.12 using the chi-squared test. So back over to our worksheet, number 5. The mean pay in 2008 of CEOs of 500 biggest companies was $12.8 million. So that was a while ago. So presumably things have changed. So a random sample of CEOs was recently obtained. Here are their salaries in millions. So we just have sort of like a bunch of numbers that are supposed to be recent CEO salaries. And this is part of the question too. Is there any evidence that the mean salary has decreased? So this decrease is sort of hinting that your alternative hypothesis should be that the new proportion is lower, but I'm just going to use not equals for my alternative hypothesis again. So which test are we going to use? Well, this time we have one piece of information for each CEO. That's their salary. So this is a one variable question. We're either doing one proportion or one sample t. The piece of information we have is a number, and we are looking for the mean. So that is not one proportion like we had up in numbers 1 and 2. It's a one sample question. So we have to get these 12 numbers. Is that 12? It's 14. These 14 numbers into Minitab and run one sample t on them. So I'm just going to try to copy and paste them 2 at a time so that I don't have to retype them or do any tricky transpose things. So I know that you can see my Word document and not my Minitab. So as soon as I get all these copied over, I'll put my Minitab on the screen. Okay, 4 more, almost there. All right, now let's put my Minitab on the screen. So I've copied these 14 numbers over into Minitab 2 at a time because the information was given in an annoying, inconvenient way. All right, so I said that we had one variable and it was quantitative, so that meant we would use one sample t. One sample, all of our data is in C9. We do not have the summarized data. We don't know the mean and standard deviation of these 14 numbers. We have the actual 14 numbers. So we put them in C9. We do want to perform a hypothesis test. The number we're comparing to is the 12.8 that was from 12 years ago. And I wanted to stick with not equals. Even though the question was hinting that we wanted to look for less than, I'm just going to use not equals every time. And do we want a graph? No, let's not bother with a graph. So I'll say okay and see what we get. We are getting a p-value of 0.376. That is not small. We do not have strong evidence that things have changed. So our mean now is 11.45. That is, like more than $1 million smaller than 12.8, but our sample size is only 14. So that's not really a big enough sample for that difference to be statistically significant. When you have a small sample like 14, there has to be a bigger gap, and or a smaller standard deviation, like they all have to be right around 11. They can't be so spread out. This difference could be statistically significant if we had a bigger sample. And then so it's sort of more evidence that that 1 million is like a real difference and not just luck. Okay, so can I squeeze another question in this? I think I can squeeze a third question onto this video. So let's flip back to Word and look at question number 6. Do college students who have volunteered for community service work differ from those who have not? So we have 57 students who have done service work and 17 who have not. And then we ask them a second question. There is a variable that measures attachment to friends. So I don't know, maybe that was based off of a survey or something, but it generates a number. Okay, so so basically, like they have some number that measures how attached they are to their friends, and this bar is supposed to be over top of the x. That's supposed to be the mean for these 57 people. So their mean score on this friend index was 105, and the no service people, their mean score on the friend index was like 96. So here we have two variables. We have the first variable, like so for each of the people who participated in this study, we know if they're in the service or no service group. So that's the first piece of information. And then we have some kind of friend score. So we have two pieces of information about them. The first information is categorical. It's service or no service. And the second piece of information is a number. So we have two types of tests that work in that situation. The first is 2-sample T, where you split into two groups and you compare the two groups. And the second is a ANOVA, where you can split into more than two groups. So because we only have two groups, let's just use 2-sample T. So we have the summarized data for the two groups. So we'll just go over into Minitab and bring up a 2-sample T test. So stat, basic statistics, 2-sample T. We have summarized data. In the first group, there are 57 people. Their mean is 105.32, 105.32, and their standard deviation is 14.68. In the second group, there are 17 people. Their mean is 96.82, and their standard deviation is 14.62. And what is it asking for? A 99% confidence interval for the difference between them. Okay, I think I mentioned in the summary for what would be on the exam that I was only going to do confidence intervals for one variable question. So this is a confidence interval question for the 2-variable one. I guess I didn't double check this review sheet before I went and started making a video. So a confidence interval for this type of question is not something that'll be on the final, but there could be, and you should expect that there might be, a hypothesis test for two groups here. So we'll just run both. So we'll get our confidence interval, our 99% confidence interval, but the type of thing I would ask you on the actual final exam is the hypothesis test for, are these two equal to each other, yes or no? So we'll hit OK, see what we get. So obviously group 1 has a higher mean. It's higher by 8.5, and that doesn't mean group 1 is always 8.5 higher. We have a confidence interval for what that number actually is, and here's where we think it could be. They could actually be like 2.74 lower, or they could be a lot higher, like 19.74. So that's the confidence interval the question was asking for. But on the exam, the type of number that I would actually ask for is this p-value. That's what I told you in the videos from yesterday. So that one is 0.045. So that's less than 5%. So it looks like we do have evidence of a difference. Okay, we don't have evidence of a difference at the 1% level. So that's the 1% level goes with the 99%. They sort of pair together. So this is bigger than 1%. So at the 1% confidence level, 4.5% is too big. But if we were testing at the 5% level, this would be small enough. Okay, since this asked for 99%, it makes more sense to compare it to 1% because those two go together. All right, so we'll end this video here and do another 3 questions in the next video.